We are so pleased to have Mara Prentiss here to discuss renewable energy. I also want to thank Yvonne Stapp, who is right over there from Science for the Public. She, the Belmont Media Center, and the library are all starting something. We're trying to start something called Citizen Literacy. This particular event is science literacy. So I would love to welcome Yvonne up here to introduce Mara.
Good evening. And Mary, thank you very much for introducing the project, and thank you for the library hosting this joint project with Belmont Media, the library, and Science for the Public on civic literacy. Tonight, we're especially delighted to present Mara Prentiss, Mallinckrodt Professor of Physics at Harvard University and author of Energy Revolution, the Physics and Promise of Efficient Energy. And I am told that all of the library copies are out. Thank you. Dr. Prentiss is a fellow of the American Physical Society, and she has collaborated with at least 4 Nobel Prize laureates, and we are lucky to get her before she gets a Nobel Prize, so we thank her for that. Her research is largely concerned with the application of physics to understanding complex processes, say, in biology. And in her book, though, for the general public, Energy Revolution, she brings her physics expertise to a major issue of our time and presents a very clear argument for energy, renewable energy now. We are very honored to introduce Dr. Mara Prentiss. Thank you so much, ma'am.
Today I come to bring you a message of hope, that there's a lot of gloom and doom going around, but I think it's not true. And so I want to talk to you about things that are already going extremely well and opportunities that we have to make them go even better. So I'm going to take a broad approach here. What I'm going to talk about is changing where we get our energy, how we use our energy, and general aspects of our lifestyle where we can make a lot of changes without sacrificing our comfort. That famously, Dick Cheney discussed not being a big fan of energy conservation, but I'm going to discuss cases where even he would be a fan. And so the idea is not to sacrifice, it's not to wear a cardigan sweater in the winter, it's to figure out how to live better and live well. So as Yvonne mentioned, we waste an incredible amount of the energy we consume. And this wasted energy does not represent when my daughter forgets and leaves the lights on when she goes, or leaves the television on. That's not it. This is fundamental loss, most of it due to burning. There's a theorem called Carnot's theorem that says the amount of energy you can get out is limited by the temperature difference between the hot region and the cold region. And you just can't do better than that no matter what you do. And so when you burn, you just have to waste a lot of energy for very fundamental scientific reasons. This isn't because people are stupid or bad engineers. So if you can get rid of this, the amount of energy you need is actually much smaller. And if my daughter can remember not to leave her lights on, we can do even better than that. So there's a huge opportunity here, and I'd like to give you some examples of how we can take advantage of this. So what's our current fuel situation? This is our division of energy. The bad news is 83% of it is fossil fuel burning. So it divides, the biggest source of energy we have is petroleum, and that's almost all cars. So this is basically transportation. Natural gas is used for a variety of things, for heating and electricity. Coal is almost all electricity and is plummeting. The coal use in the United States has been plummeting for a very long time, and it's going to continue to plummet whatever anyone does because it economically can't compete with natural gas. So that's really good news because coal emits the most CO2, it emits the most other particulates, it's the dirtiest fuel, and coal is disappearing because it's not economically viable, not because of anything in policy that people are doing. And then the remainder is divided to non-burning sources, nuclear, hydro, wind, et cetera. So how did we get to this place? Well, this is a history of energy use in the United States. So at the beginning of time, which is to say the founding of Harvard, virtually everything that we consumed in energy was wood burning. So we burned wood, and then people discovered you could burn coal. And then around the Second World War, things really took off, and we discovered we could burn everything. And we did. And so there's this huge increase in energy consumption. And you notice this dip here. And as you probably realize, this dip was the Depression. So that's an economic dip. This dip is the oil crisis. There was a huge increase in energy here. So these were political economic events. You see this dip out here? That's changing our lifestyles. That event is very different. That's a change in how we live. And I think that that's permanent, and that's a huge event that I want to emphasize a bit more. So this is the same graph as before, only instead of showing all the energy, I've shown the different types. So there's wood peaking around the Civil War. Coal goes up, and then notice it's plummeting. And it's keeping going down. Petroleum also is going down. Natural gas is going up because it's cheap. Fracking has made natural gas much cheaper, and that's absolutely transformed the economics of energy generation. The good news is that natural gas generates much less CO2 than coal does. It's much cleaner. So we have been dropping our CO2 emissions for some long time just from the economics of switching from coal to natural gas. So that's really good news, and that's purely economic. That's not driven by any political consideration. So I said I have a lot of good news for you. This is some of that good news. People worry, well, if we use less energy, then our economy is going to go to crud. But the truth is that if you look at the energy per dollar, it's been going down for a long time. We are no longer an energy-intensive economy. So the fact that we're using less energy doesn't mean we have less economy. The world economy grew last year, and the energy use worldwide went down. So this is a transformation that is not about economic catastrophe. And if you look at the energy use per capita, it's been more or less flat for a very long time. It peaked somewhere in the mid-70s, and it's been going steadily down. So energy use is going down, and it's going to continue to go down. The trends that drive this are energy efficiency, changes in technology, and these are going to be lasting changes. So this is really good news for us. So can we change? Well, we already have. What I've shown you is that we've already had a series of transformations. We were once a wood economy, then we became coal, then we became grouped. We are now making a new transformation, which is moving in the short term toward natural gas and in the long term toward renewables. And that's a purely economic argument, but it's having huge positive consequences on the climate and our health. He's using less energy because he's insulated himself. So he's not changing anything he's doing, he's just wasting less because he's better insulated. So I regard that as passive. The alternative is active. This is the way the high jump used to work. Then Fosbury came up with the Fosbury flop, and that's how it works now. Humans don't have that much more energy despite great Nautilus equipment and dubious doping practices. That the dominant change between this high jump and this one was a change in how the energy was used. They make more efficient use of the energy to get over that bar. So I'm going to talk about both of these kinds of changes. Passive is awesome, but I'm only going to talk about it for one slide. So these are some examples. You know, Greek houses look really cool. They're white, but that also means that they reflect the heat back. So you're less hot inside. Steve Chu, who won a Nobel Prize in Energy and gave me my first job, went on to be Secretary of Energy for Obama. And one of the things he said is, why on earth do people in hot climates have black roofs? that is the dumbest design. We need to convince people that white roofs are cool. So literally and figuratively. So he pointed out there's a lot you can do along these lines. You know, people are generally bright enough to plant trees in hot climates to shield them, so they simply get less heat in their house. You don't need so much air conditioning if you have the brains to put your house in the shade. Things like closing windows. This is a very common practice in most European cities. Here, I confess my shutters are screwed on. They're little plastic things. They never move. In Europe, they actually move them, which allows you to change temperature. That's very useful. This was the cutting edge of the 1600s. It's a big adobe wall. Thickness helps to keep you in. This is a cutting edge of 2000, bunch of windows. This is a really neat thing that I love. It's a Coke bottle light. It's simply a Coke bottle that contains water, and the water spreads the light, so you put it in the roof of your shack, and it has about the light of a 60-watt light bulb. And so it's a very elegant little thing. My point is it doesn't have to be high-tech. It doesn't have to be wonderful. It doesn't have to be invented in a big laboratory. Some mechanic came up with that, I think, in Brazil. And so there are a huge amount of opportunities to live better without sacrificing comfort. And so I want to think about this as things that we're going to be happier because we do them. So active options, there are two choices, evolution and revolution. Evolution means you don't notice it's changing, like when your children grow. It's like, oh, wow, they were here, they're there. How did that happen? That, you know, clearly they were changing all the time, but you didn't notice, as opposed to when you see other people's children in 3 years, like, you're an adult. And so I'm going to discuss both sorts of changes. So an example of evolutionary change is change in gas mileage. Car gas mileage has gone up tremendously over time. So even though we drive many more miles per vehicle, you can see a huge increase here, we actually are using less fuel because the fuel economy has gone up tremendously. The change in fuel economy standards had a huge impact. But it wasn't any one moment. It's a whole series of things over time that have done this. So this is evolutionary. This is revolutionary, and this is one I would argue that Vice President Cheney would have loved, because this is an old-style charger, and if you ever picked one up, they're very heavy. What's inside is a big coil of copper wire, actually several of them. And the copper wire is heavy, and it only works to change 110 volts to 10 volts, for example. So if you plug it in the US, you're good. You plug it in the UK, and you blow your shaver. So it was very limited, and it was not very energy efficient. This is the new style of charger. It actually is electronic. It contains a little switch which turns the voltage on and off. So you can go from any voltage to any other voltage. It works in the US, Japan, India, anywhere in the world. You just plug it in, and you go. And it's much more energy efficient. It's more than 3 times as energy efficient as the other one. So it's smaller, cheaper, more convenient, and much more energy efficient. So that's an example of a completely different technology. This is based on 2 copper coils talking to each other. This is based on a switch that goes on and off very rapidly. So it's completely different, but it does the same thing from the point of view of wanting to plug in your shaver or your camera or your computer. So this was a revolution. That was evolution. So I'm going to argue that we should switch all of our energy to renewables, and that we can. And I'm going to go over that here. So to do that, we need to change our sources, and we need to change how we consume things. So we need to change to basically an all-electric economy. Jet planes can't be electrical, but you can use biofuels to do it. You can use corn ethanol to make biofuel. So that, with the exception of jet planes, everything else can be made electrical. So we can have an all-electrical economy, and much of Europe is moving toward that. So why would we want to do this? National security. We send a lot of money, particularly for petroleum, to places of which we are unfond, and we would prefer to defund them as rapidly as possible. We also send money to them that hurts our balance of payments. The environment is negatively affected by burning. I've been talking about CO2, but there's also sulfur dioxide, nitrous oxide, carbon monoxide, particulates. Europe right now is very concerned with particulates from diesel fuel. Paris has had trouble breathing, and so they had to ban cars, and then people got very upset I was there over Christmas last year, and people were leaving for vacation, and they shut down the cars, and they were not happy. So it's a big problem. Germany is banning older diesel cars. So there's a lot of environmental issues. Climate, tomorrow we will be reminded of how fun that is. Health effects are a big driver in the developing world. In places like Beijing and Bombay, very rich people's children cannot breathe. And that's really important to them, so they're going to do something about that, even if they don't care about anything else. And this final one, flexibility and fungibility, if I have a certain amount of energy in my gas tank, that does not help me power my computer. I have all these different forms of energy that don't talk to each other. If all of my energy is interchangeable, I don't have to store as much of it, and it's easier to share it with other people. So burning is bad. If you go into a coma for the rest of this talk, that's the one thing I want you to remember. Burning is bad. It's bad because of the Carnot efficiency I explained to you. The temperature between the engine and the outside means that efficiency is poor. You have pollutants, carbon, heat dumping. Simply warmer because we're emitting all this heat. There's a thermal effect in cities. They're warmer just because of the heat we dump. Extraction, bad things happen with things like Deepwater Horizons. There was that enormous methane leak in California that people hadn't known about. And transport, there was the Exxon Valdez, for example, which was an unfortunate adventure. So these are all reasons not to do fossil fuels. So stop burning and do something else. As I said, the dominant reason in the developing world is they can't breathe. These are real unadapted photos. And the US used to have much more of this problem. I had a friend who was a pilot, and he used to fly into Los Angeles in the 50s. And he said it was seriously dangerous to land because you actually didn't have visibility. And how much our pollution control has really improved things. And this is just a graph of how much we have improved things. A lot of things have gone down by as much as 90%. So we have made huge changes, and the developing world wants to do that too because they don't like living that way either. And so when people say, well, the developing world doesn't care, they're just destroying everything, they want to breathe. And the desire to breathe means they're changing to renewables and lowering their burning. And that has all these other positive effects as well. So there are three issues. One is, do you want to change? This is way above my pay grade. I'm going to stay away from this. I leave that to people who do that sort of thing for a living. Technology, I argue that we can. In my book, I do a very detailed calculation, and I show it so you can do it yourself too. One of the reasons I wrote the book was I'd go on the internet and I'd read stuff, and it was so varied. It's like, who on earth do I believe? So I gave you spreadsheets. If I screwed it up, you can find out. And so it's your chance to figure out how we did this. And cost, I'm going to talk a little bit about, and basically my answer is yes. So the first thing is change the sources. Nuclear. Nuclear is not burning in the traditional sense. And so I visited France as the core country for nuclear energy. They generate 75% of their electricity from nuclear. And it's relatively cheap, 5.5 cents per kilowatt hour. If you look at what the US prices are, that's a cheap price. That's the generated price, not the retail price. That's their wholesale price. They've had no serious accidents in 40 years. They've got 20 plants. Here they are. But they have problems. They have no permanent storage either. Not only are we still trying to decide what to do with Yucca Mountain or wherever we're going to put these things, but they don't know either. So they have this many cubic meters of high-level waste and no place to put it. So that's a problem. Chernobyl and Fukushima obviously were disasters. And you could argue, well, France hasn't had a serious accident. But you have that kind of serious accident and you notice. And so people have to evaluate risk for themselves. Nuclear is a topic in which I like to say as little as possible. Scientifically, nuclear energy absolutely works. It generates electricity fine. The issues are how risk conscious are you? How risk averse? How much do you worry about these things? And what else do you worry about? The price in the US is poor, and I'll show you the cost. Nuclear is terrible. It's one of the most costly options. And there are a lot of reasons for that. I don't want to go into US and French nuclear policy, but I did want to briefly present nuclear. Hydro. The good news is hydro is an effective renewable energy source, and it includes storage. Hydro is the only renewable energy we can control. The bad news is we're using all the rain that falls in the United States. If you do a back-of-the-envelope calculation, you can't get much more hydro than we have. And if you look at detailed calculations from the Bureau of Land Management and Mines, they argue there is no more hydropower in the US. So we have all the hydropower we're going to get. And so it's awesome, but it's limited. But you can have pumped hydropower all you want. If you want to pump water up and let it fall down during the night, you can do it all you want. We just can't harness much more rain. Wind power. Wind power has the good feature of being compatible with agriculture. People say it sounds terrible, but I've walked under the wind turbines that they have in Medford, and they didn't sound bad to me. The cows look pretty happy there. So what are our wind potential? The thing about wind is some places are windier than others. So this is a wind map of the United States. Purple is good. So there's this huge belt right down the center of the country. And usually this is a political map when you see something like this, and this represents voting patterns. And the good news is they've got a lot of wind, and in fact, wind is incredibly popular there. It's actually a bipartisan thing. Iowa is the state that gets the most energy from wind. 35% of Iowa's energy comes from wind. So this is a bipartisan happy thing. There's a lot of energy there, and they are eager to export it. This is all good. Here, there is no wind power. Putting some wind turbine there is not going to get you anything. And the coasts have a lot of wind, which is why they're special. But the big wind in the US is right down that central corridor. And I have a map of where wind farms are. People aren't stupid. That's where the wind farms also are. So a brief scientific interlude. If it's traumatic, you can cover your ears and close your eyes. The important thing is that the power you get scales as the cube of the wind speed. So if you double your wind speed, you get 8 times as much power. So it's really useful to put wind farms in windy places. The same windmill generates much, much more energy in a windy place. So the political translation is you want to build really big rotors on really tall towers in really windy places. And the good news of the calculation is that we have more than enough wind along that central band to give 100% of the energy for the United States. Not just electricity, every bit of energy we use without even taking into account that burning bonus to just get the energy we have now, including all the petroleum. If you say, well, we're going to be smarter and be like Belmont and go for electric cars, et cetera, then you need even less energy. So we have more than enough wind, we are good. So solar. A number that's really popular is 1365. Don't go back through your history and wonder who invaded whom or executed whom. It's actually the amount of watts that fall on a 1 meter squared panel in space in a day. So if you had a satellite and it was always facing the sun, you would get this much power. But in reality on Earth, we only get about 35 watts. So what's the difference? Well, one difference is that the satellite always faces the sun. For us, the sun rises and sets, and the total factor you get is a factor of 4. You get a factor of 2 for darkness and a factor of 2 for your solar panel facing in the wrong direction. So you end up losing a factor of 4 for that. So this is a picture of solar panel efficiency, and now you can afford to put solar panels everywhere. The difference between the most efficient and the least efficient isn't large. Phoenix is 32 to 43. Boston is 22 to 29 watts per meter squared. So if you have a 1 meter squared solar panel, this is what you're going to get in average power out of that. So wind farms you want to put in windy places. It's really important. You want to make them big. Solar panels go anywhere. There's a little difference in efficiency, but it's not large. So you want to put solar panels everywhere, and this is a local solar panel here. So if we just put a solar panel on every suburban roof, that would be 30% of the US electrical power.
One thing is they're not good in the shade.
Indeed.
It's the one place they're not so good.
And we have to not do questions, right? Sorry. Sorry. So geothermal works fabulously, but again, you have to have geothermal power where you are. So this is where there's geothermal power in the US. Again, people aren't stupid. They put the geothermal power where it is. So this is my big science slide. We have more than enough renewable energy to supply 100% of the US power, or US energy that we use now. And if we have the burning bonus, if we take out the Carnot efficiency, these numbers are even better. So no problem, we have enough renewable energy. But this is average, and averages are important. These are a bunch of people with an average age of 45. These are two. This is a reminder that averages don't necessarily tell the entire story. And so we have to say, well, average power isn't the same as instantaneous. If I want the lights to go on in my bathroom, I want them to go on. I don't want to be told that I can wait 5 minutes. Like, no, I cannot wait 5 minutes. I want light now. So how do we make it instantaneously match? And there are two obvious big options. One is control demand to match supply. This is a place where they had a problem. I guess the lights went out in Ecuador. And so this is Ecuador having no electricity at all. All they had was their car lights. So we want to avoid this. We want people to get as much electricity as they want. So it's a question of how to do this intelligently, and of course, storing energy. If you store it, it's not a problem, and the averages become the true value. And it turns out that not only does energy supply from renewables, for example, change, but demand does too. We don't have a constant demand. What powered companies would like was a constant demand all the time. And that's most economically valuable for them. So it turns out renewables change in time is actually useful. This is actual data from the state of California. So this is the total energy consumed by California. As they get up in the morning, the sun rises. So as the energy demand increases, solar power does too. So you actually automatically match. So the demand goes up, but the supply does also. So people say, well, renewables are terrible because they change. But in the morning, they change in a really good way. And you say, well, what about at night? It's like, not so good. So at night, you have to figure out what to do. But one helpful thing is to have solar panels faced west. So another question is this too costly? And we spend a lot of money on things. This is our fossil fuel subsidy per year. This is what Hurricane Sandy cost. These we can't really place a cost on very well. The health effects are really hard to place. It's, living in Beijing is like smoking 30 cigarettes a day. It's not easy to say how bad that is. And it's really not easy to say how bad that is. But it's not good. So we want not to send more money to that particular charity. So we want to be more dependent on ourselves and more renewable. And so one of the issues with cost is we say, well, what's the cost of electricity? Well, there isn't a cost. First, there's a big regional variation. So you can see Massachusetts has a very high cost. California has a high cost. There's less cost in the center. This gives you an idea of the variation. But look at Iowa, the place that's more than 35% wind. It's the third cheapest electricity in the United States. So arguing renewables are going to drive your costs through the roof are not true in the very existent, very real, very American state of Iowa. People say, well, don't tell me about Denmark. I don't want to hear about Denmark. I don't want to live in Denmark. Like, okay, how about Iowa? Iowa's good. They've got farms and pigs and corn dogs, and they get more than 35% of their energy from wind and really cheap electricity. So this is a real American example that renewables aren't awful. And the other example of what energy costs is electricity is charged differently depending on the season, depending on the hour, depending on, in California, how much money you make. So there's a very complicated pricing structure. So all this graph is giving you is different prices for energy depending on demand. So California really socks it to you out there. It's almost 50 cents a kilowatt hour at peak demand. And Alabama has a really, really low minimum price. But the point is, that map I showed you was average prices. But you can do fairly well if you can balance your energy consumption and storage by, for example, having solar and storage and sell it back at times when it costs more. So it's important to remember there is no given cost. So a thing about renewables is you pay now, and then it's a capital expense that goes over time. It's hard to know what the future is going to be. This is oil prices, gas prices. I don't think anyone could have predicted how these things are going to go up and down. So to predict your revenue over 30 years is hard. But even now, the prices are pretty good. Right now, wind is comparable to natural gas and substantially cheaper than coal, even without a CO2 penalty or a tax subsidy. With those things, of course, it's even better. And it's not just the fuel you use. Here, all the purple bars are natural gas plants. But it depends on how you burn your gas. Do you recycle it? Do you do it in 1 cycles or 2? So all of these purple things, there's almost a factor of 2, burn natural gas. They're just different ways of using it. And onshore wind is right here. It's one of the cheapest power sources without a tax subsidy. So economically, that's why they do so well in Iowa, that it's actually a pretty good energy source. So that's the sources. We want to change consumption. And I want to argue that what Belmont does is fabulous. Electric cars are a really, really good idea. And it's because thermal losses in engines are bad. We talked about the Carnot efficiency. If you're in city driving, 63% of your energy goes to heat your hood. You know, when you put your hand on the top and it's all warm, that's not good. That was energy you didn't use to go anywhere. And when you can fry an egg on there, it's even less good. So the heat loss is terrible. With electric cars, you do much better because you don't have this heat loss. You use roughly a quarter of the energy. So by switching to an electric car, you use much, much less energy because you aren't wasting it by burning it. In the highway, it's a little less good, but it's still a significant increase. You still win a factor of 2. So what do you win by doing this? You get much less energy loss, and you don't have the burning problem. And so it's a tremendous win as long as you get your electricity from renewables. If you get your electricity for your electric car from a coal plant that is very old and very dirty, it's possible you're doing worse than a gas-driven car. So it matters where you get your electricity, but if you get your electricity from a good source, see subtle windmills that someone nicely put back there, then it's actually good. And my last thing, we have enough energy storage. Right now, today in the United States, the gas tanks in our cars store between 1 and 3 days worth of total energy use in the United States. So that's enough. If those cars were all electric, there would be no energy storage problem. That just by having all electric cars, then the average renewable energy that I talked about would even out, and we wouldn't even have to do anything else special. And so this is an example of the port of Rotterdam. They've put a lot of these things together. I compressed the science in my talk to not send you too much into a coma, but there's a lot of computer science things you can do to make the lights intelligent, to find parking spaces, to control how you use the electricity in your house. And if you put that together with solar energy and new technologies like heat pumps to replace regular heaters, we can lower our current energy consumption to something like 15% of what we're doing now without having a lifestyle loss. And some places being much more cheerful, like those little power supplies that I showed you. So that is the end of my talk then. Now we can do questions, right? Yeah.
All right, so you